Okay, next topic. This corresponds to Chapter 6 in your text. This is going to be initially charged lines. So, every problem that we've worked to date in this class has basically involved a transmission line that was discharged when we first saw it. Didn't have any voltages and currents on it. And then we flipped the switch, and as we figured out how to track the transient of bounces as it charges up to a DC level for, logic 5 volts or something like that. Well, now, what happens is if the opposite happens? What happens if you've charged something up to a DC steady state, and then you discharge? And in some ways, this is a very logical problem. At some point, you've got to turn the logic level off, right? We can't just go from 0 to 1 all of our lives. Sometimes we want to go from 1 to 0. Well, what is the discharge transient in that scenario? That's really what we're going to answer today when we talk about initially charged lines. And before getting into it, I'm going to introduce our full complement of equivalent circuits that we're going to use to describe transmission lines. So if I draw 2 bars on the board and I connect them to a circuit, at different stages we already know a couple different models that we can use in this scenario to replace it with an equivalent circuit, right? This is my basic T line. We said when we have a discharge transmission line, there are no voltages and currents on it, and we're interfacing it with a circuit that maybe suddenly energizes it. What does it look like? We can replace this, and I'll draw a dotted box around here just to denote where we're severing everything and what we're replacing. We can replace that with 2 Z0 resistors. Make nice and pretty terminal circles. And so this box gets cut and pasted into this box in your circuit analysis when you have a discharged line. When you have a DC steady state line, this is the easiest one of them all. You can plop, cut, and paste this diagram into your rectangular dotted line there. The transmission line, if it is lossy, should look like 2 short circuits connections. And that's only after all the reflections have shaken out of the system that's excited by a DC source. So those are 2 special cases. In the last quadrant here, I am going to put the most general model that you can always use as a circuit equivalent. And sometimes throws people that you can have different equivalents, more than one valid equivalent for a circuit element. But for these complicated devices, sometimes that it calls for multiple different equivalents. These are the simplest ones you can use in this case. Here's a more slightly complicated equivalent that you could use for this case, or even the transients if you're tracking the V pluses and the V minuses on the system. So that looks like this. Okay. This is not the discharge line. This is the general equivalent. Now, what is it? you got a Z0 impedance, or resistor, in your equivalent circuit in series with the 2V minus dependent source. Dependent voltage source. What does it depend on? Well, it's whatever the V minus is that's striking the end of the line at that particular moment. If you can measure V minus at the source of the line, you can plug that into there and use it in your circuit analysis. Likewise, if you move over to the load, what we've been calling the load side of the line, whatever your positive V plus is striking the end there, you can plug into here, double it, put that source in, series with the Z0 resistance, and that's how it will present itself to the circuit on the right-hand side. And so really, this is a nice model because it always works. If we have a discharge line where there's no V plus or no V minus, there's zero, these are short circuits, and we see that we get the same thing as the discharge equivalent. Interestingly, if we let this reflection shake out and we're dealing with DC voltages, then this model will energize these voltage sources, and it will turn out to be equivalent to this model. It will behave as if the voltages and the currents on the opposite ends are the same, as if you have a short circuit connection. And we'll see that as we work through one of our examples. And the reason why this is nice, because it will also work in the case where we have an initially charged line and we make a transient change. We disconnect a voltage or connect a resistor somewhere else. Do you have any questions about these so far before we get into an example to illustrate how they're used? No? Perfect understanding? Gonna hold you to it. So let's quick work through the transient of the following problem. I got an 8-volt DC source. I'm going to have an 8-volt source connected to the 60-ohm transmission line through a 20-ohm intrinsic impedance at the source, transit time of 20 nanoseconds, and 180-ohm load resistor at the bottom. Nice contrived values because the gamma sub S is negative 1/2 if you calculate the reflection coefficient between 20 ohms and 60-ohm line. And the gamma sub L is positive 1/2. If you look at the reflection coefficient between a 180 ohm load and a 60 ohm line. And let me just briefly blow through what the output voltage would look like in this scenario. Relatively easy to calculate at this point. I'm going to graph it in terms of transit times. This would be 20 nanoseconds, 40 nanoseconds, 60 nanoseconds on the time axis. And on the voltage axis, if I graph V sub L, what I will see at time equals to 0 when that source is flipped into the circuit, I'll have to wait one transit time, but a waveform is going to make it all the way down to the source, the load side, and I'm going to see a jump up to the value of 9 volts, which will persist for 2 transit times. Why? Because a fraction of that 8-volt source is going to make it onto the line. It's going to propagate down. It's going to hit a high impedance load, which we know will do strange things like make the total voltage jump up higher than the source voltage for a brief period of time, as it spawns a reflection that goes back to equalize the boundary conditions. 9 volts will persist for 2 transit times. We know it persists for 2 more transit times because it's going to take 1 transit time for the reflected waveform to go back to the source, and then for part of that to flip back to the load side. When it hits that source at transit time equal to 2, it it experiences a negative 1/2 reflection coefficient, which means the waveform that travels down the line is now negative. It's erasing the total voltage on the line, a portion of it. And so when it gets down and hits the load, this is going to jump down to a value of 6.75 volts. And that value is going to persist for 2 more transit times. Why? Because there's going to be a reflection back to the source side, and it's going to have to come reflect back to the load side before we see any more changes in the system. When it gets all the way back to the load side at 5t, what happens? Well, it was negative, it's hit the source again, that negative 1/2 reflection coefficient makes it positive again, comes all the way down, and now I got a little bit more added to the load, and it becomes 7.31 volts. And all this is fine and good. If we wanted to double check ourselves, if we want to go home late at night and double check to make sure this is all working out, follow the bounce diagrams or draw it on a paper, however you like to see it. But there's a very easy way to check this out. This transient behavior should be approaching whatever the DC steady state value should be. What is that going to be? Well, if this thing is hooked up for a long time, we know that that transmission line can be replaced with 2 short circuits connected to this 180 ohm resistor. Then the voltage that we're converging to is just the voltage divider, 180 ohms divided by 20 plus 180 ohms times whatever source is feeding it. We work that through the Magic Professor calculator, where everything is calculated ahead of time. Oh, that would be 7.2 volts. 180 divided by 200 times 8. 7.2 volts. Lo and behold, that looks exactly like the value that we're converging to. Remember, in the transient, it's going to take an infinite amount of time to shake itself out, but after maybe like 20 or 30 transit times, you won't be able to measure the difference. And you're asymptotically jumping up and down around that 7.2 volt DC waveform. Okay, now, just to prove that I'm not making stuff up about these equivalent circuits, let me give you a useful equation, 2 useful equations for transmission line theory, and then we'll plop in the general model and just make sure it makes sense. So, if you know, in all of our analysis, we've been computing forward propagating amplitudes and backwards propagating amplitudes, and then trying to find the voltage and the current on the output of the line through the load. If you already know the total voltage at the terminal of the line and the total current going out and into the top and bottom bars respectively, then you can, from that, you can actually back solve what the forward and the backwards propagating waves are. And here's 2 handy expressions that you should have in your notes for your homework. V plus, my forward propagating voltage, is going to be equal to my total load voltage plus load current leaving and entering the transmission line bars times Z naught, the intrinsic impedance of the line, divided by 2. My backwards propagating voltage is going to be VL minus I sub L, Z naught over 2. And so, in the case where I've got, on that steady state DC circuit, 7.2 volts, and if I look at my 7.2 volts, I'll also find that I have a load current through that 180 ohm resistor of 40 milliamps. 7.2 divided by 40 milliamps is 180 ohms. That's just Ohm's law at the terminals of the load. Then let's see if this makes sense. What is my forward propagating voltage? 7.2 plus, I've got 40 milliamps times a 60 ohm line, 0.04 times 60 divided by 2, what I get in this case is that my forward propagating voltage is 4.8 volts. And likewise, when I flip the sign, 7.2 minus 40 milliamps, or 0.04 amps, times my 60 ohm transmission line over 2, I get that my V minus is 2.4 volts. Now let's check. Is this consistent with everything we know about the line? Question number 1. Is my reflection coefficient positive 1/2? Yeah, it is. Backwards propagating waveform is 1/2 of my forwards propagating waveform. Does this jive with the general fancy equivalent circuit model, this DC steady state? Well, let's go see. On the source side, I have an 8 volts over here. I got a 20 ohm resistor here. According to my equivalent model, I got 60 more ohms in series and a dependent source that's supplying a total voltage of 2V minus, or 4.8 volts. Does that make sense? Oh, yeah. That's right. This is Z0, and this is our source side resistor. And of course, this is 2V minus, whatever the backwards traveling wave is at that point. Does this circuit check out? Well, let's see. I got 8 volts over here, 4.8 over here. That means there's a 3.2 volt drop across there. 3.2 volts across an 80 ohm resistor. Guess how many milliamps that is? 40. 40 milliamps going into and out of the source side of the transmission line. Now I go over to this other half of my equivalent model. Here's my 60 ohm intrinsic impedance in series with a 2V plus source. What is that 2V plus value? Twice 4.8. 9.6, right? Is that the value? Yeah, 9.6 volts. And that connects to an external load resistor of 180 ohms. 9.6 volts divided by 180 volts. How many amps are flowing through this circuit? 9.6 divided by 180, I'll do the calculation for you. 40 milliamps. 40 milliamps coming out. 40 milliamps going in. If I do the voltage divider, I'll find that this is going to be 7.2 volts. Oh, and let's do it over here as well. What's the voltage at that point? If I add up the portion of voltage here to this 4.8 volt source, I'll get 7.2 volts across that terminal. So lo and behold, this is a very complicated equivalent circuit. But when we work through the numbers, plugging in our V minus and our V plus, what we find is that it's the same voltage drop and the same current coming out and into the transmission line. It's the same voltage over here coming out and same amperage coming in and out of the transmission line. So it effectively behaves like a short circuit. So you could use either one of those equivalents for this model. Now, if it was a test and I told you that we're studying a DC steady state, which of those equivalent circuit models are you going to want to use to calculate something? The easy one, of course, of course. This is just a sanity check. It is a sanity check because now we're going to use this for a slightly more complicated problem. The case where you break the connection. So before that, let's field some questions.
Can you describe how you get amperage going into that circuit?
How do I get the amperage going into the circuit? So I've got 8 volts across that source, 4.8 across there. So what's the difference between there and there? It's going to be 3.2 volts. So I have 3.2 volt drop across these 2 resistors. They're in series. So let's do a little calculation here. Running out of board space. .2 volts divided by 2 resistors in series. One of them is 20 ohms and the other one is 60 ohms. 20 plus 60 is 80. 3.2 volts divided by 80 ohms should be equal to 0.04 amps, or 40 milliamps. Any other questions? Well, while we're at it, let's just verify the voltage as well. 0.04 times my 60 ohms is how many volts? 0.04 times 60, that's 2.4 volts. If I add 2.4 to the 4.8 that's already there, I get 7.2. Same voltage on the source side as is on the load side. Just to verify that calculation. Sorry, sometimes I get whipped into a frenzy and I skip steps. This is so exciting. Seeing all of this work out. You don't believe me. Okay, so now let's make the change that we don't know how to do yet. That we haven't done yet, I should say, because we actually do know how to do it based on this analysis that I just gave you. Let's look at the end of that DC charged line and make a break. Here's my transmission line. It's charged up to a constant DC 7.2 volts at DC steady state. And I take a switch. And now at a new time equal to 0, let's kind of shift the time axis and pretend all that DC analysis happened in the distant past. Now let's break the switch. Well, remember, this line is charged. We can't just treat it like a Z0 that we did at our initial transients in our other examples. We have a V plus of 4.8 volts and a V minus of 2.4 volts immediately before that switch is thrown. So here's the question. Which of these voltages will change immediately after I throw the switch? Will it be V plus or V minus? It will be the V minus. That's right. Because remember, the voltage that is down here at the end of the line was placed on the line 20 nanoseconds ahead of time. That same value is going to persist for the next 20 nanoseconds. In fact, it's going to persist for the next 40 nanoseconds because the thing that's feeding it on this end, on the source side, is a combination of the source and the backwards traveling waveform. The thing that's feeding this backwards traveling waveform, however, is the 1/2 reflection coefficient that existed before t equals to 0. I had 4.8 volts coming down. I got half of that going back. When I break the switch, what is the new reflection coefficient? I got open circuit. What's the reflection coefficient of an open circuit? +1, +1. Infinity minus Z0 over infinity plus Z0. Call that gamma sub nu. So now, when this is open, my new reflected waveform is going to be 4.8 volts. I got 4.8 volts coming down. It doesn't have anything to go. It gets to the end of the transmission line and goes, oh, and turns around and goes back. Right? Plus 1 reflection coefficient. So, interestingly, what does the transient of this thing look like? You throw the switch open, and the open circuit voltage went from 7.2 volts to what value? Well, twice. You got 4.8 going down, 4.8 coming back. They got a total up to the total load voltage for continuity across the junction. You got 9.6 volts. And if you want to see that, just plug in your equivalent circuit model. I've got a dependent source that's 9.6 volts, 2 times V plus, which does not change immediately after the transient. 60 ohm resistor, open circuit. So of course I'm going to get 9.6 volts across my open circuit. It's interesting to note, though, that all I did was flip a switch, and now the terminal voltage jumps up all of a sudden. That doesn't seem right. It jumps up even bigger than the source voltage, 8 volts, feeding the entire system. But remember, this is part of a transient. Transients do weird things like that. It's not going to last, because that 2.4 volts is going to go back and reflect with a minus reflection coefficient and come back and erase part of that 4.8 volts. And then they'll reflect and reflect and reflect and reflect. And what should the steady state open circuit voltage be after all those reflections shake out? Starts at 7.2, jumps up to 9.6. This is going to jump down to some value below 8. That's going to jump back to a little value above 8, and a little bit less than 8, and a little bit above 8. How do I know that? Well, because look at the steady state value for this thing. If I've got an 8 volt source, series with the 20 ohm resistor, and I replace my transmission line with the long-term DC steady state value, open circuited, I'm going to get 8 volts and no current through there. See, it's all consistent with everything you learned in circuit theory. The only difference is that there are these goofy transients that exist at very small time scales, which 40 years ago didn't matter. You couldn't even see them on your scope. But now they're critical to the data flow on the cable or the circuit trace. Okay. Yeah, Lem.
I'm not quite sure where you're getting some of your numbers from. Not your solutions, but the ones that you're plugging in with. 7.2, is that given to us as the incoming voltage?
So that was the steady state value that we came up with over here. After we had let the system charge up, the system reached this steady state value over here, which was a 20 ohm resistor in series with a 180 ohm resistor. Voltage divider formula 7.2 volts. And then that was our starting point for when we flipped the switch right there. And lo and behold, when we flip the switch, it doesn't immediately go to 8 volts. There's this weird transient on the transmission line. But you see, the steps there are pretty simple. Calculate what that steady state behavior is of your DC charge line. From that, you can figure out what V plus and V minus is. And then when you make a change, either at the source or at the load, you change your reflection coefficients and trace how that new waveform travels through the system. Let me give you a little mind-bending exercise to see if you understand this concept. Here's the problem statement. I have a long, skinny parallel plate capacitor. Something that basically looks like a parallel plate capacitor, but if it's long and skinny, we know in this dimension it behaves like a transmission line, right? And let's say it has intrinsic impedance of 100 ohms. And it has a transit time of t for a signal to go from there to there. But at the end of the day, it's just a long, skinny capacitor with a total amount of capacitance. Let's say you charge this up with a DC source to 200 volts. And then you disconnect this so that now there is 200 volts total drop from that capacitor top bar to the bottom bar, from the top plate to the bottom plate. And it's an ideal capacitor, so it doesn't lose any charge. None of the charge migrates to the bottom plate. It stays there, 200 volts DC. And you take this high voltage capacitor and you put it in your sibling's sock drawer. And so one day they're going to run in and they got a finger. And let's just say that the finger happens to be 100 ohms. You connect it to the side as they're rummaging around for their favorite socks. You connect it to the capacitor plates. Well, the question is, how long does this scream last? How long does this scream last? Well, let's take a look at this transmission line problem. As always, there are multiple ways to parse the mathematical solution of what's going on this transmission line. If, for example, you say, oh, there are 200 volts DC static across that line. You can say I take my oscilloscope on that long, skinny capacitor. I put it here, put it here, put it here, put it here. Assuming I've got near infinite impedance, I will observe 200 volts static across there. Static. It's not a function of space, not a function of time. Constant 200 volts. But that's not the transmission line way of looking at the solution. Transmission line says we need to decompose the total solution into forward and backwards propagating waves. This is like an open circuited transmission line on either end of the capacitor. A reflection coefficient is going to be 1 on both sides, right? So one way of viewing this solution is I got a gamma sub s of +1. I got a gamma sub s, or a gamma sub L of +1. What I really have is 100 volts traveling down this way, reflecting with +1 reflection coefficient, producing a V minus that has 100 volts this way, which gets to the end and has a +1 reflection coefficient and feeds back this way. And lo and behold, if I break this into two backwards and forwards propagating 100-volt waveforms that are feeding one another, I get the same solution as my static 200 volts across there. And, it's like, well, man, why would you go to all that trouble to model it with forward and backward propagating waveforms and reflection coefficients when all it is just 200 volts is standing there? And you say, yeah, that's good and fine when everything is static. But as soon as I introduce a change, then the power of my transmission analysis is apparent. Here comes the 100-ohm finger. What's the reflection coefficient of this junction? If I got a 100-ohm line, 100-ohm load, reflection coefficient is 0. My ZL nu is 0. 100 minus 100 over 100 over 100. And what I've basically done is I've shut off the waveform, the reflected waveform that's now feeding the 100-volt V minus. So I had 100 volts coming down to the end. It's no longer reflecting. It's all being absorbed by the finger. And there's 100 ohms propagating backwards on the line. And so what we find is that the transient looks like this. Let me do a sketch. So at t equals to 0, let's put 0 plus, a little bit after t equals to 0, that moment that the finger touches the line. If I could sweep really quick my oscilloscope down the line and look at voltage as a function of position for that instant, what I will see is something like this. If I were to graph voltage as a function of position, I would still see 100 volts coming down to the end of the line, but now that I turned off the reflection, V minus, it'll stop there for just an instant, and if I move a little bit to the left, I'll see the full 200 volts that are still on that line. So I have a leading 100 volt edge, leading edge of 100 volts, and a total 200 volts drop between the top and the bottom plate. And what I see is this leading edge that starts moving across the transmission line, my little long skinny capacitor. Yes, you have a question?
I was a bit confused because earlier I guess we had both ends open.
That's right.
Reflection coefficient of 1 at both ends.
That's right.
And you said that 100 was coming across the top and then 100 was going on the bottom. It was like a loop cycle.
Yeah, 100 volts going this way, 100 volts going that way, both feeding one another because the reflection coefficients were +1. That's exactly right.
Voltage was being transferred to each other just through the open circuit.
That's right.
Okay, so with this example, we have reflection.
That's right.
I'm just confused how it doesn't like go through the resistance and come across the bottom and just do the 100 cycle.
Remember, now that the resistance is there, the reflection coefficient is 0.
Yeah.
So basically 1 plus 0 is the total times the forward propagating wave, 100 volts, is going to show up across the load. So I'm going to get 100 volts across the load. Even though there were 200 volts on that capacitor, my 100 ohm finger is only going to experience 100 volts of it. And this extra 100 volts is going to erase across the line because it's your backwards propagating waveform, and there's nothing to feed it anymore. It's 0 at this junction because there's no reflection. I happened to pick a finger that was perfectly matched to the transmission line. It will wipe out, and then over time, by the time t equals 1 transit time, this 100 volts will persist all the way down here, and then this backwards propagating 100 volt waveform will experience the +1 reflection coefficient. But by the time the V minus gets to the end here that we've completely turned off, V minus is 0. 0 will reflect at the junction, and finally that last 100 volts starts erasing itself. And so by the time we get to t equals to just a little bit before 2 transit times, the only voltage left on that physical structure will be a little bit 100 volts at the end. And then finally, for any time greater than 2t, this will have expired. There will be no voltage on the transmission lines. In other words, the scream lasts for 2 transit times in this scenario. Right? We've turned off the reflection on one side, and because it was perfectly matched, it took exactly 2 transit times to shake its way out. Now, is that anything like the capacitor transient that you learned in your circuits class? This weird kind of voltage steps, kind of a step or mode that propagates through this capacitor that discharges across your figure. What did you learn happens to capacitors when they're connected to resistors in your physics or your circuits class? What kind of analysis is that? RC circuit. let's draw that briefly on the board, because I want to make a point here. I want to make a point that what I'm teaching you is not too bizarre. It actually jives with everything that you've learned so far. So, in these problems where you had like a steady state 200 volt capacitor connected suddenly to a 100 ohm resistor, you learned in your class that the transient looked something like this. You'd have your 200 volts, and then there would be this decay, exponential decay, usually to 0. And this would have a time constant of RC, right? EXP to the minus T over RC. And that doesn't look anything like the transient that I'm describing, which is like this. 200 volts, 100 volts for 2 transit times, and then nothing. But that was a very contrived example. Let's talk really about what the capacitor is doing. This capacitor, if it's a good capacitor, is a nice thick plate with very little spacing between another nice thick plate. In other words, its intrinsic impedance for that long, skinny capacitor is probably a really, really small inductance and a gigantic per unit length capacitance, right? So the Z0 is actually pretty tiny, maybe milliohms or something. I don't know, it depends on the geometry. So usually, between your finger and the capacitor, there's going to be a big mismatch, right? You're going to get a really strong reflection coefficient from your tiny little Z0, and by comparison, your extremely large R finger, R sub F. And the reflection coefficient is going to be like 0.9 something something something, positive 0.9 something something. So in that case, what does the transient look like? Steady state analysis is the same. I got 200 volts, 100 volts going this way, 100 volts going that way, each feeding one another with positive 1 reflection coefficients at the end. But when I put the finger on there, it's not going to discharge in 2 transit times. Now I've got, instead of a +1 reflection coefficient, I've got a 0.9 something something reflection coefficient. And so what does my transient look like in that case? Well, it looks like this. 200 volts. That very suddenly, and for a short period of time, 2 transit times to be exact, becomes 190 something volts. And then a little bit later it becomes 190, a little bit less volts, and so forth. And you stair step down over time, and what actually you find is that that's geometrical decay, right? Every 2 transit times I lose the same fraction of a voltage. So what I actually get is a geometrical series, which if you stack them together, those stair steps together, and you kind of step back and kind of look at it at a different time scale, looks like an exponential. And if you work through the math, it turns out that the time constant for this thing is actually the same as, it's related to the reflection coefficients times the little transit times that are discharging. And from one time scale, this capacitor problem looks exactly like your RC circuit. In fact, this probably will be, it will be unlikely that your sibling's finger is perfectly matched to this particular transmission line. This will much more likely be your transient. It's interesting, though. You probably didn't know that about your capacitors. There are these weird discrete modes of discharge that exist on them, and you would never see with any of the cheapo oscilloscopes in your 2040 lab or 3040 lab, or 3041. Is that? Yeah.
Okay, so I think so what you were saying earlier is that the transmission lines were initially like itself discharged.
That's right.
You're using the finger to discharge it.
Yes.
Last thing I'm kind of caught up on is like how is it that it's starting 200 and then like 100 is getting wiped out going back, so you see 100 at the load end. But how is it specifically 100 going back when the reflection coefficient?
The 100. How is it that 100 volts go back on that line?
Coefficient 0.
Okay, so a good thing to do now, let me just repeat that one step, but now let's use our equivalent circuit model because that might make it a little more clear. When that capacitor is charged up to 200 volts, then my equivalent circuit, 2V minus voltage source, well, I said there's 100 volts coming this way. And so that equivalent source is going to be 200 volts. And that is in series with 100 ohms. And so at DC steady state, this is one of the equivalents that we could use to model that. I got 100 ohms coming this way. That makes a 200 ohms, 100 volts going this way. That makes a 200 volt source. And I can see I'm going to get 200 volts here, 200 volts here. No amps coming in or out. No amps coming in or out. We can see that I could replace this with 2 straight lines, and it would be 200 volts across there. Now here comes the 100 ohm finger. In this circuit diagram, now I've got 200 volts, which isn't going to change, because remember, the V plus that got put on this line has been traveling down there equivalently since one transit time at least, being reflected from this junction over here. So I still have 200 volts, still have 100 volts striking the end. Now I've got to divide it over 2 resistors. So that's why immediately as the finger touches, this immediately drops down to 100 volts. Now, immediately as the finger touches, and that's the key word, immediately, it means that just a tiny, tiny fraction of a femtosecond after I make the change, this V minus isn't going to change either. Because this V minus waveform got put on the line at least one transit time ago. And so I can still use this to model the other end of my transmission line until at least one transit time elapsed. And so that's always the key point. This is one thing that confuses students when they start putting this circuit model into their analysis of transmission lines. This V minus is the V minus observed at the end of the line. This V plus is the V plus observed at this end of the line. And never the two shall mix. Just be careful, because V minus has changed as observed from the front end of this line as soon as that finger touches. And eventually this becomes 0 when that reflection stops feeding the backwards propagating waveform after one transit time. So it becomes 2 times 0. 2 times 0 is 0 volts. And now, one transit time later, this side doesn't see any voltage. And the remainder of the 100 volts, no longer being fed by a reflection, wipes itself out and expends itself across the finger. What did you say?
It's a negative 1 coefficient at the end.
Well, no, it's a 0 reflection coefficient over here.
Oh, yeah, you're right.
Yeah, but and that looks like an erasure, right? It's basically a single forwards propagating waveform that is no longer being fed by any sort of source or reflection. Just turns itself off. Okay. Well, good. When we come back on Thursday, we are finally powerful enough in our transmission line knowledge to work a problem, a type of problem that will surely be on your test. The infamous sequencer problem. I will work one example of that. And it's beautiful because it tests everything. Steady states, discharge lines, charging, discharging. Okay, so now let us begin by doing a little recap here. What do we know how to do in this class? We know how to analyze realistic high-frequency signals, high-speed switching logic signals on time domain transmission lines. How do those lines charge up? How do they introduce reflections? How does that distort a signal? And also, how do they discharge? That's what we talked about yesterday, which is or Tuesday, which is just as an important part of the problem. If you go from low to high, you got to be able to go from high to low in logic. And so we talked about initially charged lines. And now we are to the point where we can work some types of problems which I like to call sequencer problems. And if you understand them, you understand most of what we covered, because they incorporate things like cascades, fan-outs, switchings, discharge lines, pre-charge lines, a variety of different equivalent circuit models. And so I am going to work through one example of a sequencer problem. You've got 2 on your homework to give you some additional practice. There's like a half a dozen in your book and online on the tests as well, in addition to that, that you can play around with. So pay attention. The next 20 to 30 minutes are critical. Then once we've got that down, we're going to talk about short pulses, not just DC switched pulses, but short pulses and short finite duration waveforms on transmission lines. And then by the end of the class, if we have time, we'll introduce the concept of reactive terminations, which is a type of termination we haven't dealt with yet, but comes up quite a bit in chip design and high-speed and circuit analysis. Okay, let me go ahead and introduce the concept. And these problems look a lot scarier than they really are. If you understand the basic concepts that we've gone over with, the equivalent circuit models, what they mean, when to use them, these are actually pretty easy. But they look intimidating. And so let me go ahead and give you an example sequencer problem. So in this circuit, we're going to have a 12-volt source, a 3Z0 source impedance that connects to a transmission line with impedance Z0, which has another switch at the end of the line. So this is switch A, and this is switch B. And then there's a fan out to 3 more transmission lines, each with impedance Z0. This one is a matched termination at the end, the one that goes down. I got a length up here that's also Z0. This is also matched with the Z0 resistor at the end. And let's see, I've got another segment running out of board space here. Here's a transmission line, a short stubby one, with Z0 impedance and a Z0 resistor at the end of the line. So that one is also matched. Oh, and just to make things interesting, we haven't talked how to do this yet, but might as well start to get things interesting. I am going to put a capacitor across there. A capacitor of value C. So let me label a couple of key voltages that I want to look at during the course of the operation of this circuit. V sub A and V sub B. There's going to be a voltage at the front of this line. I'm going to call it V sub X. Voltage here, I'm going to call it V sub Y. And I'm going to have a load voltage at the end of the line, V sub L. And so, what we're going to do is we're going to work through different combinations of switching in this complicated fan-out circuit. And here are basically a summary of the different states. State 0. Both switches are open. everything is discharged. So there are no voltages and currents on any of the transmission line. All four of them are dead lines. State 1, immediately after switch A closes. And that word immediately is key. It means less than one transit time, a small fraction of a nanosecond afterwards. How does the circuit immediately behave in that scenario? Then the next key phrase in this, in state number 2, switch A has been closed a while. And that term, a while, electromagnetically speaking, means all of the transient behavior in reflections and capacitors charging up and everything has shaken out of the system. We've waited long enough so that they're behaving as their DC steady state circuit components. So that's going to be state number 2. State 3 is immediately after switch B closes, when that charge is flips down. And then state 4 is switch B has been closed for a while. So those are the 4 states. The first one is kind of trivial. And it's important to work through them in order. If we switched the states around and closed switch B first and then close switch A, we get different results. So we're going to work through this case by case. And what I'm going to do, usually with these problems, there's a table that you have to fill out. And so in here, on this board, I'm going to go ahead and draw our table, which will contain the answers. We're going to need voltages VA, VB, VL, VX, VY, and then my states are going to be over here. I have state 0, 1, 2, 3, and 4. So I have a grid that I have to populate with values. And of course, the first state is trivial. All the voltages are 0 because we have a dead line. If those were blank, you would have just gotten 1/5 of the problem right. Usually I give those to you, the trivial ones though. So you can't score points making trivial answers. Okay. State number 1. Immediately after switch A closes. So before you do any analysis, take a good common sense look at this circuit and understand what a transit time means. Because most of these entries do not change when you only change one part of a transmission line circuit. So let's go over here to the circuit diagram and look at this. Immediately after switch A closes, always ask yourself in these problems, what is going to change? Well, VA, the voltage I measure at the terminal of the line, clearly that's going to change. What about VB? No. What about VX? No. VL? VY? We just got free points just for using common sense. You laugh, but you'd be surprised how many people don't get that step right. So let's just go ahead and add. Nothing changes, so we'll just copy down these values, 0, 0, 0. The only thing that does change is that our initially dead Z0 transmission line model, which looks like this when we put in our dead line equivalent, is connected 3Z? Yeah, thanks. To our 12-volt source. And so we use a simple voltage divider equation. A quarter of the series resistance is here, so a quarter of that voltage is going to be there too. That means 3 volts. Keep my units off there just to keep the thing from being too overly cluttered. So that is immediately after switch A is closed. Now when switch A is closed for a while, let's go back here and figure out what charges up. Here's our circuit. It connects into this line. This line is going to charge up. Right now, this open circuit keeps the rest of this network disconnected from this transmission line. So I'll charge this guy up with reflections, but these other 3 lines have yet to be excited until switch B closes. And so in the steady state, what I have is a short circuit pair of wires connected to what is basically an open circuit. So in that case, VA should be equal to VB. And what's more, all of that 12 volts is going to be across that open circuit, because I got an open circuit in series with 3Z0. Does that make sense? So let's go ahead and write that into our state diagram. I got 12 volts here, 12 volts here, nothing, nothing, nothing. See, these are easy, right? No problem. This is always the hard step, though. We now have a charged up line with 12 volts across it. Immediately after B closes, it looks like all hell breaks loose in the circuit. I got capacitors, I got 3 transmission lines and fan out. What is going to happen to this network? Okay, first of all, let's deal with this capacitor issue. When I connect a DC voltage to a capacitor, what does it initially look like? Good, good. Short circuit. Good memories. So effectively, that shorts out. If you go back to this diagram, this capacitor will look like a short circuit, which will effectively remove these two transmission lines immediately after B equals the switch B is closed. So those will not initially charge up. After a while, when that capacitor starts to get voltage across it, then there will be some reflections that shake out in these other lines, and they'll approach a steady state DC value and charge up. But we don't have to worry about that immediately after B closes. Really, immediately after B closes, the only thing that's connected to the output of this transmission line is this dead transmission line. So I'm going to use my dead line model, 2 Z0 resistors, to replace that transmission line. And I have to use my charged transmission line model for this particular one because this already has voltage over it. So this is the trickiest part of the entire analysis right here. State 3, the circuit diagram that I'm going to use to analyze this is going to be 12 volts. $3Z0. I'm going to need a charged equivalent for that first transmission line. We know that to be Z0 in series with a dependent voltage source. That is 2V minus. Whoa. And then I have another dependent source with Z0 impedance that's 2V plus on the other side of the line. That's connected through a closed switch B, a capacitor, which looks like a short circuit at this moment, and then it's connected to a dead line equivalent model for that second transmission line. Z0 in parallel with Z0. I don't even know why I drew that part of the circuit. That's not doing anything. Yeah, do you have a question?
Where'd you get the 2 volts? The 2V minus and 2V plus?
Those were the equivalent circuit models that I presented last class period. They'll give you the equivalent behavior of the transmission line in a circuit. Now, the only other thing we need to figure out is what are V minus and V plus. Well, I gave you some equations to do that last time. We could use them, or we could use common sense. Let's do both just to make sure. Remember, in the previous step, step 2, I had an open circuit before the switch B closed. The reflection coefficient for an open circuit is +1. So I had a voltage waveform coming back. I had the exact same voltage waveform going this way, reflecting back with +1 reflection coefficient. My total voltage were 12 volts. Therefore, I know through common sense that V plus must be equal to 6 volts, and my V minus must be equal to 6 volts. Furthermore, just by making a switch change, these two values don't change, my V minus and my V plus, because these were already put on the line one transit time before. It's going to take at least a transit time for either of them to change. Or I could use the equations, right? We know that if I have a V plus and my load is 12 volts, I have to add IL Z0 and divide by 2. Oh, there isn't any IL. This is 0 because it's an open circuit. So clearly this is 6 volts. And likewise, V minus is equal to 12 volts minus IL Z0, the equation we covered last time. Again, 0 volts. Oh, this must also be 6 volts. So it doesn't matter how you solve it. There's always more than one way to skin the cat in these transmission line equations. My recommendation to you is use both ways, learn both ways, learn the equation and use the reflection coefficients and common sense analysis, and use one to check the other on the test. It's always nice to have a consistency check. Okay, so this is going to be 12 total volts. This is going to be 12 total volts. So I have 12 volts, and I got a Z0 here and a Z0 here. And I'm looking for VB, and I've got a Vx that I have to calculate. In fact, these are the only two voltages that are going to change in this step. The other voltage, VL, is and the VY are removed on the other side of this short circuit, so they're not charging up, they're not changing. And the VA actually isn't going to change either, because I didn't change the topology of the circuit connected to the line, and I'm not changing my backwards propagating wave yet. So I can keep that the same. So really all I need is VB and Vx. And lo and behold, with this short circuit in the system, they're actually the same voltage, right? The drop here is going to be the same as the drop across that resistor. There's basically two wires connecting them. So I solved for one, I solved the other. It's a simple voltage division. I've got 12 volts here, so I must have 6 volts here because it's equally divided across a Z0 and another Z0 resistance. Did everybody see that? It's really 6 volts. So let me put that in. VB is 6 volts. Vx is 6 volts. We said VL is 0 and Vy is 0. They don't charge up yet because of that shorting cap. And this doesn't change. VA doesn't change because the change needs at least a transit time to propagate back down the line to make any voltage disturbance. So immediately after that switch is thrown, the 12 volt open circuit jumps down to 6 volts, and a 6 volts appears at the terminal of that second transmission line. Other than that, we're done that step. That's not so hard, right?
I got a question.
Yeah, sure.
If A has been closed for a long time, right?
Yeah.
And we found that VA and VB were the same thing, right?
Mm-hmm.
So then if the ZO over there goes away, it's like a short. There's really no difference between point VA and point VB, so shouldn't they be the exact same?
There's no difference between VA, the voltage at the left-hand side of the line, and the right-hand side of the line, VB, when the system is in a steady DC state. But as soon as you make the switch change, it's no longer in a steady DC state. We're introducing a transient, and we'll have to wait for all the reflections to shake out of the system before they are the same voltage.
Oh, so I guess I was thinking that once A closed, and then after a while, and that goes into like steady state, you can just almost forget about the ZO.
Yeah.
Two short lines.
For state 2, that's exactly what we did. In that model, we used a 12-volt source, a 3Z0 resistor, and then we just had two straight lines that were ended as an open circuit. And in that case, VB is the same as VA.
Right. Now, if you drew if you left that right there, right?
Mm-hmm.
And then you drew a little switching up there, and then put another ZO, which would represent that angle, that part up there at the top.
This one?
Uh-huh.
Mm-hmm.
And put that on the end, and then connected the bottom of it right back to the bottom of VB.
Mm-hmm.
Then basically, as soon as that closes, you should have a voltage divider over that ZO and the 3ZO. Wouldn't that in between those still stages straight?
No, you're confusing the models here. Because as soon as you make that connection, this is no longer a valid circuit model.
So then it causes the reflection pattern. Okay.
Exactly. Then we have to resort to the more complicated one over here.
Yeah.
I would much rather use that other model too.
Just keep going, moving.
Yeah, I would love to use that model too to analyze it, but unfortunately, it's only for a limited condition of DC steady state. Okay, so let's do this last line. And again, nice thing about these problems is that your steady state states are usually pretty easy to calculate. All you got to do is turn all of your transmission lines into short circuits and just do simple circuit theory. And in a way, every other state in these problems is usually one of those steady states. So, it sort of gives you some ability to reset your answer. And so errors don't typically propagate downward. Unless you're really confused in these problems. That's good because you don't get double jeopardy, right? You'll make an error up here and then lose all the problem points later on. So, okay, let's do that last state. Now, all the switches have been closed for a long time. The capacitor, as it's charged to a DC steady state, becomes a what? Open circuit. So we can remove it from the equation. All the transmission lines become short circuits. Here's our first transmission line. Here's our second transmission line, terminated in a Z0. Here's our third transmission line that's short-circuited, terminated in a Z0. And here's our last transmission line, short-circuited, turning into a Z0. So this is the final steady-state DC value. We're going to look for what is the voltage at point A, voltage at point B, voltage at X, voltage at this L, and voltage at Y. And this is actually not very difficult to analyze here, is it? We've basically got a bunch of voltage dividers. Here's 1/6 of the total series resistance. The total series resistance is 6Z0. This is 1Z0. So 1/6 of this voltage should appear across here. It should also appear across here. And it should also appear across here. So that should be 2 volts, right? 2, 2, 2. Here I've got 2 plus 2 plus 2 volts, so my voltage across here should be 6. And that's the exact same voltage as at the start of the line, so that should also be 6. And voila! We have just finished what looked to be a nasty problem. But as long as you attack it systematically and use your proper transient or steady state equivalent circuits, you can polish this off. Yeah?
How does VA and the being 6 as well? Is it just because it's a short circuit?
Yeah, that's right. This is all effectively one node in circuit analysis, which is difficult because in different points of your transmission line analysis, those aren't the same node. In the transient analysis, they're not the same node, but in the steady state, they are. Yes?
So for state 3 for VA, would you explain it like using that little picture over there that's behind you?
Yeah.
Yeah. So if there's 12 volts there and a 12 volt power supply there, then wouldn't that case have to be 0?
Well, remember, VA is the voltage from here to here. I've got 6 volts coming back, which means this source is going to have 12 volts total. So I have 12 volt rise from here to here, 12 volt rise from here to here. There's actually no potential drop between these resistors, so I don't get any current going through them. And so the voltage in between them is also going to be 12 volts. We sort of made the hand-waving argument that said, oh, well, the voltage just isn't going to make it back there. The change that we made over here isn't going to make it back there until one transit time later. But you can see if you use the circuit models, it's still equivalent. That's another good way to check your answer, just to make sure the common sense is holding up. Any other questions? Well, great. Oh, yeah.
Can you repeat again what you did there, minus?
Could you speak up, please?
Sorry, can you get the V minus equal to 6 again?
The V minus, how did we figure out that was 6?
Yes.
Okay, so at steady state, V minus is equal to, we have a general equation which will tell us, you basically look at your load voltage minus your load current divided by Z naught over 2. Do you remember this equation from last Tuesday? Load voltage is 12 volts. Load current is 0 because it was open circuited before that switch came down. And then you just get 12 over 2 is 6 volts.
Okay. So,
good question. Okay.